Hi everyone, welcome back. Today we're doing binary tree right side view. This is a binary tree question and it touches on the concept of pre-order traversal. So we're given the root of a binary tree and we have to imagine yourself standing on the right side of it. So we are standing here and we have to return the values of the nodes you can see from top to bottom. So in this case, if we look from the right side, we can see that 1 is the rightmost node on the first level, 3 is the rightmost node on the second level, and 4 is the rightmost node on the third level. So at this point of time, we will return an array that is the same size as the height of the tree. So in this case, the height is of height 3, and in this case, we return 1, 3, and 4. If we are given a binary tree that is 1, now, and 3 nodes like this, then in this case, the height of the binary tree is of height 2, so we return 1 and 3. 1 on the first level, 3 as the rightmost node on the second level. And if we have an empty binary tree, then we return nothing. So the number of nodes in the tree is in the range 0 to 100. And what this means is that it is possible for the root passed to us to be empty. Like it's possible for it to be empty. And every single value in the nodes inside the binary tree would have a value from negative 100 to 100. So one approach to solve this is using a variant of a preorder traversal. So to all viewers that are new to the concept of preorder traversal is where you recursively check yourself first, you visit yourself, and then you visit either the left or right, and afterwards pretty much the two neighbors that you have for each of these nodes. So for this approach, since we want to prioritize the nodes on the right side, we will be using a variant such that we visit the right side nodes first. And the objective is ultimately to populate a list where for every single height, you have a position in the list, and we will keep track of what is the first node that is visited on each level. And we must be visiting the nodes in a right priority fashion. So by doing a pre-order traversal where you visit yourself and then subsequently visit the rightmost subtree, then you are pretty much going to visit the rightmost elements first. And the idea is that if we visit the rightmost elements first, and these are the elements that we see first, then we will put them into the final right side view list and we will return that as the answer. So that's pretty much the essence of that approach. That was quite a lot of words. Hopefully it will be clearer as we implement it. So the first step will be to define the final answer. So the final answer will be right side view, and this will be a list of type integer, the same type as the output of the function. And this right side view will be expected to have the same height as the binary tree. So the length of this list is the same as the binary tree. And this list will contain the rightmost nodes in each level. So if a node is visited first with pre-order traversal priority right, then that node is the rightmost node in that level. That's pretty much the essence. So once we're done, we can start implementing the pre-order traversal. And this pre-order traversal would have two parameters to implement this algorithm. The first would be the current root that we're looking at. This is the tree node that we are currently visiting. And the second is the current height of this root. So we will set this to 0. And this pre-order traversal will return nothing. We will also define another helper method. Let's call this height visited, and this height visited will take in a height and it will indicate whether if we currently visited that height. So this would just be return length of right side view less than height plus 1. And to our viewers that are wondering why do we do height plus 1, is because this length over here is not technically 0 indexed. If your list is of size 1, then this is going to return 1. But your height might be 0 in this case. So this height over here is 0 indexed, and that is why we must add it by 1 to compensate for this length not being 0 indexed. So that's pretty much it. And the essence is if not height visited, in other words, this current level is not visited yet, then what we would do is we will append this right side view with this current roots value. In other words, we will set this current node as the rightmost node for that level. So once we're done, that's pretty much it. So this over here is pretty much mimicking the visiting logic of pre-order traversal. So we visit ourselves first. And after we visit ourselves, then the next thing would be to call pre-order traversal on the right node and followed by the left node of the current root. So we will do so if root.right exists, then we will do a pre-order traversal on root.right and we will pass in height +1. So this is pretty much the same height as the parent function, and we just increment it by 1 to indicate that the subsequent node has a height +1. And similarly, after we visit the rightmost element, then we visit the leftmost element. So pre-order traversal root.left height +1. And that's pretty much the algorithm. So to do this, to implement this, we will do pre-order traversal on the root. And once done, this pre-order traversal will do all the necessary traversals, and at the end, this right side view will be mutated correctly such that this right side view contains all the right side view nodes for every single level. So we return this. So before we submit, let's quickly trace this out with a simple test case. So in this case, let's start off with this binary tree over here. So let's start tracing here. And let's define a call stack, because this approach that we are using is a recursive algorithm. So let's use a call stack to trace where are we at each function calls along with where we left off before we invoke another function recursively. So the first function that we'll be calling is preorder traversal on root equals to tree node at 1 over here. And the height in this case will be equals to 0. So we are here right now. So is the height visited? In this case, the length of right side view is currently 0 and is less than 0 plus 1. So this is true. So I guess thanks to the tracing, I realized I messed this up, did I? Yes, I did. So this should be more than equals to 0, sorry. I just got it inverted. So in this case, 0 more than equals to 0 plus 1. Yup. Actually, is there... Yeah, should I just invert this so that it's more readable? Yes, maybe I should. So let's just call this not height visited. So the mistake that I made was that I inverted the logic here. Like, I should have flipped the signs for height visited, but perhaps it's better for us to just do this so that we do not confuse ourselves during technical interview situations. So in this case, at the very start, the length of right side view is 0, and the height that we are given is 0 plus 1. So in this case, 0 is indeed less than 0 plus 1. So in this case, this is indeed true that the height is not visited yet. So let's call this height not visited yet. Yeah, this might be best. Yeah, this is way more readable now. So now length of right side view is 0, less than 0 plus 1. So this is true. And because this height is not visited yet, we would append the right side view with root.val. So currently, right side view was initially an empty list, but since we append it with the current root.val, so we will put 1 inside here. So we're done with this approach. Now, if root.right, let's see if 1 has a right side node. Yes, it does. So it has 3. So we will create another preorder traversal invocation for tree node 3. So, but before we end off, let's quickly keep track of where we left off. So we will add root.right. So this is just to let me know that after we terminate this function call, we can continue at root.right for this evocation of preorder traversal. So now this would be 3 and height will be 1. So we are evoking another function call on the call stack over here. So now we are back here. And in this case, let's check whether if height is not visited yet. So length of right side view is now 1 and height is 1. So this is true. So the height is not visited. Like this current level is not visited yet. Actually, yeah, let's just call it height not visited yet. I thought it was a little confusing, but okay. So since it's not visited yet, let's append right side view with 3. So now we have 1, 3 like this. And we can move on to line 29 and line 13. So at this point, let's check 3. 3 indeed has a right child on the right. So let's call preorder traversal on 4 as well. So similarly, we end off at root.right. So let's call another preorder traversal over here. So now this is pointing at 4 and height is now 2. So now we're back here. And over here, in this case, let's quickly check whether if height is not visited. Height is equals, length of right side view is now 2. And the height is 2 plus 1. So this is indeed still not visited. This third level is not visited yet. So we will visit this node right now. So we will append 4 into this right side view over here. So once we're done, we will check our right side. In this case, 4 doesn't have a right child. So we save a function call by not calling it if root.right doesn't exist. And same for the left side over here. So in short, we're done with this function call for preorder traversal. We're pretty much traversed all the way from 1 to 3, 3 to 4. And now we can terminate our function call at 4 and return back to 3. So let's terminate this and let's continue. So now we are at the preorder traversal function call for 3 node 3, and now we are over here. So because 3 doesn't have any left child, we can terminate this. So over here on root.right, now we are back at preorder traversal for this call over here. So now we are done with root.right. Let's do root.left. So actually, as I trace this out, I realized that perhaps we could terminate this tree if we know that the current length of right side view is already the same as the height of the tree. That said, it's possible that your left subtree has more nodes over here. So there is no way you would know what is the height of the binary tree without actually visiting all nodes. So scrap that thought. We still have to unfortunately iterate through all nodes in the left subtree regardless. So now we are at root.right. We have finished that. So now we are at root.left. So since the node 1 over here has a left child, we have to unfortunately do another preorder traversal continue the preorder traversal on the left child of 1. So height is equals to 1, and let's continue with this. So in this case, height is already visited. In this case, this will evaluate to 3 less than 1 plus 1. So this is not true. So we skip line 27 and line 28. So now we are at 2. So we will now make a traversal to root.right on 2. So let's continue to 3 node 5, and the height is 2 over here. So now we are at 5 over here. So let's check whether if the height is visited for 5. The length of right side view is now 3. The height is 2. So this is not true. So we will skip line 28 and line 29. And because 5 doesn't have any left and right child, we will skip these 2 parts as well. And in short, we're done with this function evocation. So we will traverse back to 2. And over here, we will check whether if 2 has a left child. 2 doesn't have a left child, so 2 is done as well. So at this step, we have successfully visited both both itself, the right and the left child of 3 node 1. So we are pretty much done. So we will terminate our call stack, and we are done, and we return the answer 1, 3, 4, which corresponds with the answer. So this approach looks like it works. With that, let's run this code and see if this... Oh yes, I forgot one thing, did I? Yes, that's also... It passed this test case here, but if I recall correctly, we also have to check whether if not root. So if not root, then we will just return an empty list over here. It's because it's possible for us to receive no nodes in the tree. So in this case, we should return back an empty list. So yep, this looks great. Okay, let's submit this. And there we go. So over here, let's quickly discuss the time and space complexity. So if you let n to be the number of nodes in the binary tree, then in this case, the time complexity will be O(n). That's because we have no choice but to visit through every single node to figure out what is the height of the binary tree so that we know how many nodes we have in the right side view. In summary, because we are doing a pre-order traversal or DFS search across the whole tree, you are going to visit every node. So the number of traversals or computation you need is going to be O(n). For the space complexity, it's going to be OD, where D is the height of the binary tree. And in this case, D would be equals to N in the case of an imbalanced binary tree. So space complexity in this case will be O(n). And for completion, the reason why space will be OD is because we use the call stack to keep track of all variables and memory used in each function call or pre-order traversal, as well as keeping track of where we left off as we context switch from one function invocation to another function invocation. So unfortunately, we would have a space complexity of OD or ON. So with that, that's pretty much it for this question. I personally feel that this question is a great practice for our viewers who wish to refresh themselves on pre-order traversal or DFS search on binary tree questions. So I hope this was useful. If you like it, please give us a like and subscribe, and we will see you in the next video.